In this lecture, we will study the concept of Lorentz field in dielectrics. In the case of dielectrics, whenever we apply a field, macroscopically the field is the sum of several fields, and we observe a field E. But microscopically, the field observed by all individual atoms or molecules in the dielectrics has several parts. We will study the idea of this local field in this lecture. In this lecture, first we will talk about local field, concept of local field and significance. Here, the meaning of local means the field experienced by individual atom. Then we will study how many fields are here and how the fields are contribute to give you overall results, and finally we will get the expression for local field. Stepwise we will discuss this. The student will learn about concept of local field, the field that is experienced by each atom of the dielectric. The student will learn about how to calculate this internal field, how to take a small atom, then assume the surrounding field, and stepwise expression to obtain this. Molecular field in dielectric medium. This is the electric field which is responsible for polarizing a molecule of dielectric. And this electric field is represented by EIN, E internal. Actually, as a matter of fact, dielectrics material are made up of molecules and atoms. And whenever we apply an external field on dielectrics, the outer or macroscopic area, we observe that there is a displacement electric field and there is a polarization. And due to the polarization, we observe induced charges on the surface. But individually, if we talk about individual experience of each molecule or atom, then we can calculate field on each molecule or each atom, the electric field which is actually responsible for polarizing this molecule. And then we sum all the results to get the total electric field. Whenever we keep a dielectric material in electric field, as we know, the dielectric materials are not having any free electron. They are having bound electrons. As they are having only bound electrons, Then to accommodate the applied field, the internal molecules, the molecules, basic constituents of this dielectric, try to accommodate this effect. This may be accommodated in terms of displacement, maybe electronic displacement, maybe ionic displacement, or rotation. It depends on the material, what material it is. So when a dielectric is placed in electric field, its molecule become electric dipole, and molecule oriented in the direction of field. The properties of dipole depends on the material, whether it is a ionic material or a permanent dipole moment material or other. This electric field, which is responsible for polarizing a molecule of dielectric, is called local field EL or internal field EIN. We use a term as per our convenience or as per the uh, application base, but this is local field. We will try to learn the how to get this expression here. But this local field is different than the applied field. But, and this local field is originated due to application of some external field. That is all. Let us study this. Suppose a dielectric is placed in uniform electric field between two parallel plates. The dotted lines show the boundary of dielectric which are oppositely charged. The electric field experienced by the molecule of the dielectric at the center of cavity may be this E1, E2, E3, E4. Suppose we can draw here this is your parallel plate capacitor and dielectric is placed here like this. If this plate is positive, then this plate will be negative and this will be induced positive, and similarly we have negative here. Now consider a molecule at the center and try to get the field on this molecule A. I am considering this molecule inside this circle and naming this suppose A or C, whatever. Now we can calculate electric field at this point, and we can show here the electric field may be of these kinds: E1, E2, E3 and E4. What is the meaning of E1, E2, E3 and E4? We will discuss in the coming slides. Actually, there are four contributions on this field from applied field to other. We will discuss this in next slide. First contribution is E1. E1 is the primary electric field, the electric field that is applied by us. The electric field due to charge parallel plate with no dielectrics. Suppose we are having this parallel plates and we applied here electric field E, and due to this the surface charge will be, here we assume as sigma. Now if the surface we are applying electric field and the surface charge is sigma, then field can be written as Q over epsilon 0 A. We did this in the previous lecture, that this is our field sigma over epsilon 0 or Q over epsilon 0. So this is the first contribution due to the main or the primary electric field that is applied, and the primary electric field is E1, then this will generate sigma surface density and so can be written as sigma over epsilon 0 or Q over epsilon 0 A. This is the first contribution to the field. Another contribution is E2. This contribution is coming from intensity due to induced charge. The first contribution E1 is from the applied electric field, and this contribution is irrespective of any dielectric material placed in the parallel plate capacitor. But in our case, as we place a dielectric material in the parallel plate capacitor like this, then there exists a induced charge on the surface of dielectrics like this. This charge is opposite to the applied charge. And the field due to this charge, induced charge on the surface of dielectric, is termed as E2, contribution due to induced charge, that is E2. And we have quoted here, this charge will be, if this charge is sigma p, then field can be written as minus sigma p over epsilon 0. Sigma p is the surface density of bound charge. Minus sign here showing that this field is opposing the first field E1. So this is our second contribution. Now we have third contribution, the E3. E3 is the field intensity on this molecule. Yes, we have considering every field on first molecule, as we have discussed in the previous slide, due to another atom contained in the cavity, because there are certain surrounding atoms. We are assuming a cubic structure of, so if we are assuming cubic structure of this our dielectric material, then E3 will be 0 because of symmetry, because from all the sides the material, the surroundings are symmetric. So E3 can be considered as 0. But mind this E3 is the contribution due to other atoms contained in the cavity. We have considered a spherical cavity, so we are discussing on that. Here we are considering 0. Now the next is E4. E4 is the field intensity due to polarization charges as the surface of the cavity and was calculated by Lorentz. This is the field due to polarization charges. We have to calculate this field at the surface of the cavity. So finally, we have introduced 4 contributions. Just summarize this. We have started with the work, then applied electric field is not exactly the field experienced by any molecule or atom of the dielectric. In fact, the field is different, and we want to study that local field. To do this, we have assumed a parallel plate capacitor and we placed a dielectric inside that. Now, on any particular atom or molecule of the dielectric, we can assume that the atom may have an electric field which is actually the sum of 4 electric fields, E1 plus E2 plus E3 and E4, in which E1 is the field due to bilateral capacitor plates. It means E1 is the field which is actually applied. Second is E2. E2 is the field due to induced electric field on the surface of the dielectrics. Third one is E3. E3 is the field due to other atoms which surround this considering atom. And in our case, for the sake of convenience, we have assumed E3 0 by assuming our structure of the material as cubic. For cubic, due to symmetry, E3 can be considered as 0. Now we have with E4. E4 is the field due to polarization charges at the surface of the cavity, and this was calculated by Lorentz. So in the coming slides we will study how to calculate E4, as E1, E2 and E3 are known. Lorentz has given a interesting way to analyze, to obtain this E4 contribution. What he said, suppose you want to measure, actually again remember this, there is a dielectric, then there is a parallel plate, then there is existence of dielectric material, then we have an atom, and we are studying this atom here. In this atom is surrounded by many other atoms, and if we take a smallest sphere here, as we have taken here, then In this sphere, we have both charges, positive and negative. To calculate electric field, we have taken a small strip here that I am routing here. If we take this strip and try to calculate electric field, because the electric field can be calculated, this is the direction of P and E2, then we can integrate. First we will calculate electric field for at one point, then for this ring, actually this ring we will like this. So we will integrate on this, then we will integrate on sphere. First is charge density on point ds. Induced charge density we will calculate on ds. ds is this element. And if the direction of P is this, then the charge density can be written as P cos theta. Why P cos theta? Because the angle is theta. Here we are considering angle theta. And for ds, small element, the angle is d theta. So in that small element, the charge can be written as P cos theta. Now, the charge on elementary area ds can be written as charge basically equal to charge density into area. We have started here, charge density is P cos theta. So the charge will be P cos theta ds, because ds is the area. If we know charge on small area, then we have done this in the past, that we can calculate the radial electric field. Yeah. And this radial electric field actually is equal to 1 upon 4 pi epsilon 0. Actually, this is the field due to a ring. So dq over r square. And dq we know this. So we can do dq over r square. We can place the value of dq over p cos theta. So the actual DER is equal to 1 upon 4 pi epsilon 0 P cos ds upon r square. Now, this DER radial can give you the idea of internal field, DIEN. And internal field is equal to DER cos theta. So we use this again to calculate internal field, small part of internal field. So this speed, again we have taken cos, and this is called 1 upon 4 pi epsilon 0 P cos theta ds upon r square. Now this is ds, surface area of the element, and ds can be written as circumference into width. We know this, that r cos theta is the radius, circumference will be 2 pi r sin cos theta sin theta. R sin theta is the radius of this ring that we have taken initially, and the width of this is r d theta. So ds is equal to 2 pi r square sin theta theta. And from there we can calculate our field, and the field, in the field, if you write this ds, if you use this value here, the answer will be this. P cos square theta 2 pi r square sin theta d theta upon 4 pi r square. If we arrange total electric field by integrating E4, and as you can see from the figure, the angle will be from 0 to pi, then E4 can be written as 0 to pi integral of E4. And if you integrate this, you will get P upon 2 upon epsilon 0 cos square theta sin theta 0 to pi integral. We know cos theta, and if cos theta is equal to t, suppose assume, then sin theta theta will be dt, and you can find out this. E4 can be written as P upon 4 to epsilon 0 minus 1 to plus 1 to minus 1 t square dt. Actually, this limits have been converted as we convert change cos theta to t, then you can change the limits also. Then d upon 2 epsilon 0 t square to by 3. If you change the values, and finally you will left with this answer, P upon 3 epsilon 0. This is your fourth contribution. So now we have calculated fourth contribution also. If we put all the contribution here, first, second and third, then this will be the answer. D upon 4 pi epsilon 0 minus P upon epsilon 0 plus P upon 3 epsilon 0. And we know D is equal to P plus epsilon 0 E. So it is there. And this is Lorentz field equal to local field. So in this lecture, we have calculated local field on a particular molecule in dielectrics. And we have studied what are the total many contributions E1, E2, E3, E4, and calculation of E4. Thank you.